to show you kind of work through why these relationships exist the way they do. And I'm not 100% sure on circle 3. I didn't sit down and investigate this, but my thought is that there's a little bit of calculus involved in the best way of proving why example 3 or case 3 is a true case. But case 3 is kind of a special case scenario of number 2 there, middle picture. Because we talked how secants, as we move the intersection points of secants closer and closer, the secant merges into a tangent, right? Okay. So at some point, when the 2 points are really close to one another, but not the same, you still have a secant. And you have a secant, or an angle created by a secant, and another secant. So I guess what I'm saying is that in number 3, in picture number 3, maybe the iteration before that, the picture just before we got to picture number 3 would be very similar to that, except for that blue line would be a tangent, but the inside portion would be very small. Does that make sense? We want to make that inside portion infinitely small. And that idea of talking about things that are infinitely small is a calculus concept using limits and that kind of thing to maybe prove why this theorem works for that third case. But we can use some real easy geometry that we're aware of to prove why these two formulas exist the way they do. And then, like I said, a little bit of calculus maybe gets this one to transform into that one. But all this first one means, is in every circle, whenever you intersect two chords, your two chords are going to cut each other up into 4 separate parts, right? Okay. What this is saying is take the 2 parts from the blue chord, find their product, and that should equate to the product of the 2 parts from the red chord. Okay. So A times B should equal C times D. Okay. It's not all that hard to look at and realize using this picture here. I've got right here, I've put in what GC is times GD. So GC would be that distance there. Maybe we called that A in the last slide. And then GD would be that there, and maybe we call it B. So I've got it multiplying those two blue sections together. Does that make sense? And right there, it's giving me that number, 13.45. Right here, if I hover over that, it should give me EG times FG. So EG, maybe in the last slide we called that C, and then FG we called D. So this one here, this number, is multiplying C and D together, 2 red components. Does that make sense? What are you recognizing for this particular set of chords? What do you recognize about those two numbers? They're equal. Yeah. So this is saying that AB and CD from the last slide, those equate. If I start moving things around, if I start moving these points, come on. Okay, now obviously the different components that make up these products. So if I move that one around, is EG right there different than EG right there? Yeah. But when I look at the products of those two things, okay, are they still the same? Yeah, they're still 18.04. And as I move that point around, looking at just these two numbers, those are the ones I'm interested in. If I start moving those around, are they always equivalent to one another? Okay. Now, if they don't intersect, then there's a problem, and we'll see why there's a problem there when they don't intersect. But let's talk about that triangle right there and that triangle right there. What do you know about this angle where my cursor is in comparison to that angle where my cursor is? They're the same. So you got an angle congruent to an angle, right? Look at that angle right there, and look at that angle right there. You now have a second angle in the top triangle congruent to the second angle in the bottom triangle. And if I look at the last ones, they're congruent, right? And that exists no matter where I put these things. We're going to have
40.82, a 40.82, a 29.64, 29.64, and then our vertical angles. So are these two triangles, or what is the relationship between those two triangles? Let me ask you that. They're similar, aren't they? They're not congruent because I can make one a lot bigger than the other one, right? Okay. But they should be similar by angle, correct? And if they're similar by angle, doesn't that mean that there are certain side lengths that are proportional? Okay. So when I look at this, what happens is that EG is proportional to GC. EG, which is, where's EG? EG would be this one here. It ends up being proportional to that one there. If I divide those, I get a ratio that ends up, or their corresponding sides, I guess, in those two similar triangles. And then if I look at that side compared to that side, that's DG and GF. If I cross multiply, I get EG times GF, don't I? Well, EG times GF is that right there, isn't it? It might have been our C times D in the PowerPoint. And then if I cross multiply these, I get GC times DG, GC times GD. Does that make sense, everybody? So these properties, these formulas that we're getting here, they're really nothing new to us. We've dealt with similarity before, okay? We've dealt with those two triangles being similar and how they relate to one another and how we can multiply means and extremes, and they equate, okay? So when we look at this formula here, all we're saying is that the cross products are equal. The product of the extremes is equal to the product of the means, okay? But it exists inside a circle, which is kind of interesting. This one here is really the same idea, okay? Now, the way you're going to see me write this, or maybe not write it, but say it, if I look at W plus X, that is the entire secant, isn't it? And W, is that the outside part or the external part? You might hear me say external. Is Y plus Z the other entire secant? And is Y the outside part of that? So you might hear me say, when I see that picture there, I'll say entire secant times outside part equal to entire secant times outside part. Okay? Because I don't know, maybe in the next question, instead of using X, W, Y, and Z, they might use A, B, C, and D. They might use M, N, O, and P. They might use 2, 3, 4, and R. Okay? So it's nice to be able to look at the whole thing compared to the outside part, and then the whole thing compared to the outside part. Okay? But kind of give you an image of this. Just kind of running through what I've done here. It's kind of messy just to glance at, but anything that is blue, so that anything that incorporates blue is referring to the whole secant, okay? So E to F is that whole blue secant, which is 12.8, okay? And you're seeing that number right here, 12.8, okay? Then I'm going to multiply that by the outside blue part, so the solid blue one, okay? And you see it, that's 7.057. So on this side of the equation, I'm taking EF, the entire secant, times the outside part of the blue. And then it's equating to the entire red secant, which would be E all the way to H, multiplied by EI, which is the outside part of the red secant. Does that make sense to everybody? So instead of using like X and W or X plus W and all that kind of stuff in the PowerPoint, using the segments that are defined here. But if I multiply those together, that's what's happening here. So it's taking those distances and multiplying them together. And you see that all four of those distances are different, right? Not a single one of those four values are the same. But when I multiply them together, what does their product become? The product's the same, right? Okay. And that's exactly what the theorem is saying. The entire secant times the external part is equal to the entire secant times the external part. And as I move those around, as I move and change the secants, you see now the left-hand side of that equation is the side that's values are changing, right? But doesn't that, by the formula, by the definition or the theorem that we talked about, doesn't it say that these two things have to equate. So if I change this one, but I don't change the other one, the other one stays as a product of 90.438, these two numbers have to adjust. One's going up and one's going down, but they adjust in relationship to one another so that their product is still 90.438. Okay? Same thing happens if I move that one. The right-hand side changes. Okay? So how do I get this 90.438 to change? I got to change the overall secant length, don't I? And the overall secant length is dictated by where E is. And now you can see all the values changing. But when I stop, what's the relationship between those two numbers? Still the same, right? Okay. Now, why does this work? There's some. Let me just try to hide some values here, or hide some labels. I think I can. That should be enough. You see that triangle there? And do you see that triangle there? Do they both share angle E? Yeah. Okay. Now these two lines, I'm going to prove a point here with you. Is that line there parallel to that one? Is GI, that chord, parallel to that chord? No, right? Okay. So that angle right there is not going to be congruent to that one. Does that make sense to everybody? So angle like EGI is not going to be congruent to EFH. But if I start putting in some angles here, let's look at that angle there. And now I'm going to put that angle in. Are they congruent? Yeah. And then if I put that one in, is that 55.6 congruent to that 55.6? So we've got this purple triangle, and we have, I guess they're both kind of maybe purple, right? Let's go with the blue one. And then the purple one, they have angle in them, okay? Therefore, we should still have proportional sides. When we do a little bit of cross multiplying, we see that we get the idea of this formula, where it's an entire secant multiplied by the outside part equal the entire secant multiplied by the outside part. Okay? So these are kind of like these would maybe be the extremes in our proportion for similarity, and these would be our means. Okay? So that's how that's proven. This thing here is the same concept, okay? But now this tangent is no longer an entire secant times the outside part. What happens is that we get essentially the tangent times the tangent. Okay, we're going to square it. We're going to multiply it by itself. Okay. And the reason for that, like I said, it's a calculus concept. If I demonstrate this for you real quick, the calculus concept is the fact that if I look at right now, just looking at this kind of this yellow one here, let me change the color of that so you can see it a little bit better. Okay, would you agree that E to H is a secant? And as I move this, as H and I get closer and closer to one another, as H and I get closer and closer to one another, as long as this says a numerical value right here, other than 0, I know that this is still a secant. Does that make sense? Because when that distance is 0, that means H and I are on top of one another, correct? So I'm going to try to move these as close to one another as possible. And obviously, if you can see any of that dotted line, it's still a secant because it's still a secant, even though this goes, I've only got it rounded to 3 decimal places, so once it goes 0.0000, it's just going to put 0 in. Does that make sense? If I go more decimal places, still a distance there, correct? Okay. But now look at, so I'm going to zoom back out. Okay. So what I'm trying to say is that this thing here, this bottom line here, is still a secant. Does that make sense? Because there's still a gap between I and H, even though it's a very, very, very small gap. So if it's still a secant, let's look at this product up here. And I'm going to go to see 5 decimal places. There we go. this side here, so this product here is this top secant. So let's, it's that entire secant times the solid black part, which would be that stuff there. 200.3 is that product. But if I look at this side here, look at these two numbers. Are these two numbers, are those two numbers different? 14.15295 and 14.15293. Are they different? And the reason they're different is because I and H still is a segment, right? It's a very, very, very small segment. So the entire secant compared to the outside portion, the entire one is just that 0.00002 more than the outside portion. Does that make sense? Well, when I make I go on an H, and I make that distance IH go to 0, those two numbers that I have that blue box around, those two numbers should end up being the same distance, shouldn't they? And if they're the same distance, then it's a distance times itself, which is a distance squared, isn't it? Which that distance then is respective of a tangent, so that's where we get that tangent squared on the right-hand side of that equation. Okay? So hopefully you recognize, and that all that discussion there is a discussion that, if you didn't follow or didn't understand, will make so much more sense after you get a year of Algebra 2 under your belt, after you get a year of college algebra and trigonometry under your belt, and you enter calculus. That concept is like talking about how, adding, two numbers to a third grader is. And they understand it pretty easily, right? Okay, so the more math you have, that will make a whole lot more sense. But I do want to show you and explain to you that this is not just pulled out of thin air. There is purpose behind that formula. It does exist for a reason. It is true for a reason. So how does this help us? Where do we use this? You're going to see questions that do look like, and if you've seen these in your homework, if you did open last night's homework, if you guys were able to get into, I don't know if I messed your period up as well, but they give you questions that kind of look like these two, and we'll do the one on the left first. But essentially all you have to do is take that picture and compare it to either case 1, case 2, or case 3 in those formulas. So hopefully you realize that this one here on the left is case 2, right? Those pictures mimic each other. And this is the reason why I don't like to use specific W plus X times W is equal to Y plus Z plus Y, because there's no W, X's, and Y's down here, or Z's down here, right? There is a Y. But I don't know, what do I call 6? What do I call 8? I don't want to have to reference back, okay, 6 is the W, 8 is the X. I don't want to do that. Does that make sense? Okay? So I remember entire secant. What is that entire secant going to be? 14. And now what is the outside part of that secant? 6. So it gets that thing right there pretty easily for me, right? Now if I do the bottom one, okay, it's Y plus Z, which that was entire secant. So what's the entire secant here? 7 plus Y. Okay, make sure we're adding them. Okay, and now what's the outside part? 7. Okay, so now we should be able to solve that, right? That's a multi-step equation. Multiply these together, you get 84. Gives you 49 plus 7Y. 35 is equal to 7Y. Y ends up being 5. And I go through that a little bit quicker than normal, but I think you guys can do that algebra. If Y is 5, can we check this? Can we plug back into this thing here and see if we get a true statement? Okay, you said this was 14, right? 14 times 6 is equal to, now Y plus Z, or the entire secant would be 12 in this case, right? The outside part is 7. What's 12 times 7? 84. What's 14 times 6? 84. Is that all right? So then the last part as well, the last question is the same idea, but now we're going to see, let's see here. Everything, there we go. Kind of froze for a minute. Let's look at this one. If I've got these two things here, these are the same, right? So now this side here is the same concept as the last one. It's the entire secant times the outside part. So what is the entire secant here? What's 16 plus 8? 24. Okay. What's the outside part of that secant? 8. And now what is your tangent part? Z. And you would square that. Okay. That's 192 is equal to Z squared. So radical 192 is equal to Z. And then maybe you start breaking 192 down. Maybe you look at that and recognize that 64 divides 192. Does anybody know that? So it's that. What's the square root of 64? 8. Okay, so Z is 8 radical 3 in that situation. I don't think, if I was a betting person, is the end of course exam going to ask us about these types of things? Probably not. That's why I'm kind of going through them quick. I want you to be introduced to them. It does get you practice at looking at similar triangles, that kind of stuff, which the end of course exam will talk about. But it also incorporates this algebra where the end of course exam will probably ask you to do a little bit of radical work maybe. Okay? Okay. Thank you. So when we look at that kind of stuff, guys, your algebra is going to be important too. So that's why I want to talk about these. And as I work through 192, and it's happened all day, people grab their calculators. You guys do know. I've said this before. You do know there's a portion of that test that you cannot use a calculator, right? Okay. So hopefully, in practice for that, then, maybe we should not use our calculator every single time. Okay. So that being said, let's.